I think everybody has joined us, and if some people come in late, that's no big deal. Hopefully everybody can hear me. Audio is provided for the internet. Please make sure your microphone is muted. Also, if you have any questions throughout the webinar, on the side of your screen, there's a question box. I will try and look over periodically throughout the webinar. I usually get on a roll and don't necessarily take a look at it. But if you have any questions, I'll definitely take time at the end and answer all questions at the end. Also, everybody that registered today will receive a printout of the slides, and this recording of a webinar will be provided on the exida YouTube channel and our exida website. So today we will be talking about comparing mechanical failure rates. Quickly about me, my name is Loren Stewart. I'm a CFSP. I graduated from Virginia Tech in mechanical engineering. I started my engineering work in design and manufacturing, and then moved to exida. Here I work with our mechanical customers, doing FMEDA's safety assessments. I'm also researching stiction and the 2H initiative and database. A little bit about exida. We are all over the world. So wherever you are or wherever your customers are, we have a location close by. So we can help you, we can help your customers, everything that, everywhere you are, we can get to quickly, and we are available for you. Once again, a little bit more about exida so you know a little bit about us. These are our main product and service categories. So we have consulting on IEC 61511 and ISA 99 for control system security. We do product certification for functional safety, which is IEC 61508. We do security lifecycle, cybersecurity, functional safety. So we certify products. We also do training on process safety, control system security. We do it over the web. We do on-site, off-site, so you can come to us, we can come to you. However you want trained, we want to help you. We also have engineering tools, lots of software for alarm management and alarm rationalization. We have SIL selection, LOPA, SRS, SIL verification, proof testing. We have SIL stat, which is a database. It has you create your database and helps you decide when proof testing should be. We have SCA and safety case tools along with our Excellentia. We also have textbooks, databases, tutorials, reference books, market studies, anything that you need for information, including webinars and blogs. And finally, we have professional certification. We have our CFSE and CFSP program and our Control System Security Expert, or CFSE. A little bit about our engineering tools, although I kind of just went over this. We have our alarm management. We have our FACS, our SIL selection tool, our SRS tool, SIL verification tool, proof test specification, and our data collection tool, which is SIL stat. And we're proud to say that we have authored most industry references for automation and safety and reliability. And we've authored the most comprehensive book on functional safety in the market. So what we came to talk about today, some of our key points. We're going to quickly explain IEC 61508 and how it does include mechanical devices, although some people like to believe it does not, but I will show you. How exida failure rates compare with those noted in industry databases and in field studies, different ways to get the failure data and an explanation of each option and what are realistic failure rates for mechanical devices. So a brief overview, what is functional safety per IEC 61508? So functional safety goal is the automatic safety function will perform the intended function correctly, or the system will fail in a predictable or a safe manner. And that is our main goal. So a lot of people say that IEC 61508 is an EEPE standard. So it was written based on EEPE systems. The first E being electrical, the second E electronic, and the PE is programmable electronic. Therefore, people ask, what about mechanical products? Does it matter for mechanical devices? And the answer is absolutely. So combine this with the need for analysis of a complete safety function, including all elements that are mechanical. It's not just possible to meet IEC 61508 and industry-specific standards like IEC 61511 without including all mechanical products. Oops, hold on one second. Sorry about that. There we go. Can you see my screen again? Good. So the question is, how do we know it is including mechanical? So I often tell people, just Google it. And the first thing that pops up is IEC frequently asked questions page. And as you can see, the fourth most frequently asked questions involves mechanical safety related systems. And of course you can't see the tiny print here, so I'm going to expand it. So this talks about that safety critical mechanical devices must be included, and they would be considered a low complexity EEPE safety related system. And you can still comply with the requirement of the standard. So you do not need to meet the electrical or the programmable electronic requirements, but you would still meet the requirements for safety-related systems. So how does this work? IEC 61508 is based around a safety life cycle, and this is a detailed section of the design phase. And as you can see, you're going to have manufactured safety manual and the safety failure database going in to the SIF conceptual design and reliability along with safety calculations phase. So there's a need for realistic failure data for mechanical components because it feeds right into the safety life cycle. And if you do not have realistic failure data for mechanical components, you will not be meeting the SIL level that you actually think that you've achieved, or the risk reduction factor. But some people say there's no such thing as a realistic failure data, but many others are confident in their failure data. So where does failure data come from, and how do different methods compare? And this is going to be the main subject of our webinar. So there are two fundamental techniques for getting failure data. You can, first of all, the failure rate estimate technique is estimating a lambda or a failure rate based on failure data, or you can have your failure rate prediction technique based on test results for design strength and analysis. So we're first going to look at the estimation technique. So failure rate estimation techniques are estimating the lambda or the failure rates based on failure data. And there are three methods in doing this. There is the manufactured field return data studies, the industry databases, and the end user failure data studies. And each of these has their own pros and cons. So with the manufactured field return data study, you can not know what percentage of actual failures are returned to the manufacturer. If it is what some people would consider a not as expensive part, there's a good chance that the customer will just throw it away and just get a new one instead of reporting the failure to a manufacturer. And there's also different definitions of failures. Some manufacturer would think that one scenario would be a failure, while another manufacturer would say, of course, that's not a failure, that was misuse. The next technique is the industry databases. So these gather field failure data from a group of different companies, and this started in the 70s and the 80s, typically military or telecom based. One of the main examples would be ERIDA. And finally, the last technique for the estimation method would be end-user field failure data studies. So this would be a quality data gathering system can provide excellent site-specific data. And there are many existing systems that are weak, though. So we're going to look at each one of these individually. We're going to start with the manufacturer field return studies. So the positive is this is real data. It is actually coming in, and that is a huge pro. The not so great things about the manufacturing field return studies are that the calculation methods vary widely. You don't know what percentage of actual failures are returned, like we just talked about, and the definitions of failures are different per different manufacturers. So many manufacturers classify return items as a failure only if the manufacturing defect is found. Many return items are marked no problem found or it's a systematic failure, so it doesn't count. Calculations are sometimes done where operation hours are estimated based on shipping records, and it is assumed that all failures are returned. Once again, that's very optimistic. However, the data can be valuable to identify root causes and compare to establish the lower bounds of failure rates. The next one we're going to look at is industry databases. The positive, once again, is real data. It comes from multiple different customers. The negatives are there's not a lot of data available. Once again, there's different definitions of failures. You're going to categorizing and merging technologies at the same time, and there's a lack of fault isolation. So one of the examples of the industry database, the most common example, is ERIDA. And this is an offshore company from the North Sea. It's operated by DNV in Norway. It's a data analysis by SINTEF in Norway, so SINTEF. It provides useful data on process equipment, and it is kept up to date with the latest public release in 2009, kind of 2010 version of it. They are actually coming out with the newest version any day now, so we're waiting for that release. So taking a look at what's inside ERIDA in the industry database, you can see that it provides a total failure rate based on a given population and recorded operating hours. So just to, I don't know if you can see this clearly, but this example for a pressure transmitter has a population of 32 units, which equates to 1,122 unit operating hours, and states a total mean of failures for operating time as 420 hits. The next technology is end user field failure data studies. And field failure studies with sufficient information represent a rich opportunity to obtain failure rates and failure mode information about a product in a specific application. So that is a major plus, that it's in that specific application. Once again, it's real data, so that's a huge pro. Minus would be there are variations about the amount of data collection. Once again, there's a different definition of failure, and I'll explain more about that later. They're categorizing and merging technologies, and the lack of fault isolation. So after performing dozens of studies, exida experience recognizes that data collection process varies by order of magnitude or even more. Some of these could be when a fault report is written, what is the definition of failure, are as found conditions recorded during a proof test, what are the operating conditions. And these are just a few things that can make the data collection process vary so significantly. So we talked about in the previous slide the different definition of failure. And a huge part of this comes from, is it random or is it systematic? So random failures are a failure occurring at a random time, which results from one or more degraded mechanisms. A systematic failure is a failure related in a deterministic way to a certain cause, which can only be eliminated by the modification of the design or the manufacturing process or the operational procedures, documentation, or other relevant factors. So as you can see, this is kind of where a gray area in the standard almost. So we wanted to see if there was a consistent interpretation. So we actually sent out a study. We sent out a questionnaire to a large amount of people on the exida mailing list to answer different scenarios and what they thought the answer was. This first example, as you can see, it was a failure occurred when a de-energized to trip remote actuated valve snapped closed and shut down the process during normal operation. The failure was traced to the PLC logic solver rated to 50 degrees centigrade, where an output module failed to de-energize. A component in the output module, a transmitter, had failed such that it could no longer conduct current. The ambient temperature was quite hot. It was 55 degrees centigrade. An X-ray of the transmitter showed that a burned out bond wire was likely due to an electrical overstress. So sending this out to the group for the survey, 4% thought that, okay, this meant it was the end of life. It was no longer in its useful life and it should have been pulled earlier. 39% said, no, this is a systematic failure. It was either designed improperly or there was a problem with manufacturing. And 57% said it was a random failure. So you can see over half would say, oh, this counts as a random failure, but almost 40% of people wouldn't count this in as a random failure, or it wouldn't count as a failure in their studies and in their reporting. This next example shows that 57% thought that this actual example was systematic, where 43% said it was a random failure. Once again, about half of the people over half of the people, 57%, wouldn't include this as a random failure in their reporting. So the second way of getting failure data is predictive methods. So failure rates, as you can see, something better is needed than just receiving estimated. So prediction failure rate technique is predicting a lambda or a failure rate based on test results or design strength analysis. So there's two methods of doing this: the B10 point or data, or an FMEDA. So the B10 data is based on cycle testing for mechanical or electrical mechanical products. And this assumes that the application has a constant dynamic operation. An FMEDA is a predictive technique developed by engineers at Exida. It uses component database that accounts for design strength versus a predefined environment. So taking a closer look at the B10, or the cycle test failure data method. As we said, the B10 method uses cycle testing data, and a cycle test is done on a set of products. Should be over 20 sets until 10% of the units under the test fail. And this number of cycles unit failure is called the B10 point because of the 10%. The B10 number of cycles is converted into a time period by knowing the cycles per hour in any particular application. So a failure rate is calculated by dividing 10% of the failure count by the time period. So this lambda D, or dangerous failures rates, is assumed to be 50% of the total, and the safe failures, or the lambda S, is assumed to be 50%. And it is assumed that no other failure modes exist. It's just dangerous or safe. The B10 method assumes that the constant failure rates due to useful life is entirely to premature wear out, and all other failure methods are insignificant. Research shows that other failure modes become significant when these products don't move frequently. And some failure modes become significant if a product is static or motionless for over 100 hours. So comparing the B10 failure data for solenoids or actuators, because we're in a mechanical webinar, when the O-rings and other seals are part of a product, many failure modes become significant when the product remains static for a week or more. This includes stitching, cold welding, corrosion, binding, a lot of different things. And most of these failures are dangerous. Therefore, the B10 data is not applicable to most applications, including the process industry applications. So now we're going to look at the second method, or the FMEDA, which is failure modes, effects, and diagnostic analysis. So FMEDA is a predictive failure rate method developed by engineers here at Exida. It performs a study of each component and how component failures will affect the device. So an estimate, or test how well the automatic diagnosis and proof test will detect the component failure. So FMEDA's analysis is done per a well-defined set of environment criteria, or even more than one if applicable. This page out of our book is a component failure rates are a function of operating in the environment. Therefore, the FMEDA analysis is done for the defined environment. So it could be profile 1, which is cabinet mounted. Profile 4, subsea, profile 5, offshore. And profile 6 is process wetted. So as you can see, there's going to be different failure rates per each component for the different profiles or environmental criteria. So an FMEDA is using a component database, failure rates, and failure modes for a product. So a transmitter, solenoid, actuator, any of those. And they can be determined through an FMEDA. A useful life can be predicted, and a proof test coverage can be predicted. This is showing a snapshot of an FMEDA result, and this analysis shows differences in design, applications, and operating conditions. So as you can see, the table on top is a double port guided valve in clean service. It's broken into fail safe, fail dangerous undetected and no effect, or close on trip, a full stroke or tight shutoff, and open on trip. As you can see on the bottom graph, it's the same valve in severe service. Once again, it's divided into fail safe, dangerous undetected, no effects, or full stroke, close on trip, tight shutoff, and open on trip applications. The accuracy of a FMEDA method depends on the accuracy of the component database. So the component database must include failure rates and failure mode distributions for each component as a function of one or more operating profiles for the environmental profiles. And useful life of each of these components must also be listed as a function of the operating or environmental profiles. Therefore, the component database must be based on and calibrated by field failure. The exida database for the components are calibrated by 150 billion unit operating hours of field failure data from the process industry. And as you can see, there's the failure data calibrates the component failure database, and that's used in FMEDA analysis. The FMEDA results are then fed in to compare the product to level failure rates per mode, and that is compared to the field failure data. So where does this 150 billion operating hours come from? It includes all three sources of estimated failure dates: the manufacturer field return data studies, the industry database, and end user field failure database. So now let's get into how does each method of failure rate data compare. And the best way to show this is visually, at least for me. So we're going to start with ARETA, which is very reputable, and look at their guide on pressure transmitters. So the ARETA data provides a total failure rate based on a given population and recorded in operating hours. This example for a pressure transmitter, there were 32 units and over a billion unit operating hours, or sorry, a million unit operating hours. And it states a total mean failure rate for an operation time is 420 fits. So comparing pressure transmitter failure rates, you can see we looked at FMEDA results from 35 different pressure transmitters, comparing it to ARETA, which is the industry data, and also the end user field failure data, or the DAO data that we have received. Overall, the exida FMEDA results are very close, or somewhat slightly pessimistic, or as I like to say, conservative, with a slightly higher failure rate. As you can see, each one of the blue triangles is a different FMEDA. And looking at different designs, some designs are going to be more complex, some designs are going to be simpler. And as you can see, that's accounted for each FMEDA. And you have the exida FMEDA average along with the DAO field failure data and the ARETA field data, the mean of the ARETA field data. The next example that I would like to look at is a solenoid control valve. This example actually has a population of 4,718 units, which is a lot of number of units that they looked at. And the estimated failure rate for operation time is 760 fits. So looking at a comparison of solenoid control data, we have the exida FMEDA average. We have the exida average, along with some extra different examples of the FMEDA. We have 3 spool solenoid valves. We have two poppet solenoids. We also have the Dow field data, and we're comparing this actually to manufacturer warranty data. As you can see that you can understand how we say that it's very optimistic to assume that you're getting all of your returns back, because that's just, if that were the case, the manufacturer warranty data would be much higher. We're now going to look at a comparison of actuator data. We're going to look at the Dow plant study, a couple of different exida FMEDAs. You're going to have a rack and pinion. You're going to have a double rack and pinion spring return and double action. You're going to have a diaphragm air to open, Scotch yoke, our average, along with another certificate, which is a manufacturer data, and a method that we're not quite sure what they did. Once again, you can see the Dow data and the exida FMEDA average, along with individual FMEDA results for the actuators, the manufacturer warranty data, and another certificate data. If you take note, I did not include the exida data for an actuator. exida actually compares valve and actuator combinations. They don't have it broken out into actuator data and valve data. But we can look at the valve actuator combo. Here we have 1,111 units with the failure rate being 1,010 fits for a valve actuator combo. If you look here, we have different triangles showing the different FMEDA examples. We have some of our generic numbers along with some of our actual failure data, along with the exida failure data of the valve and actuator combos. And just to show all of the failure rates again, we have the manufacturer field return data study. We have industry databases and user field failure data study, the B10 method, and the calibrated FMEDA method. As we kind of found out, the manufacturer field return data studies, you don't get all of, you don't know what percentage of actual failure rates are returned, and you don't know what each manufacturer is going to say a failure is. There's quite confusion. What's systematic? What's random? What is counted in these studies? And also for different process safety and non-continuous or high-demand applications, the B10 or cycle testing is not applicable. But we do have industry database and user field failure data studies and calibrated FMEDAs, which would be useful as we've seen a comparison. They're all ending up about the same. So that's going to wrap up this session. If you want more information, we have the free web seminars on our website and also a YouTube channel. We have lots of white papers. We have our SAEL, which is our Safety Automation Element List, and we have books on our website. There's ISA books, and you can always email me. I'm going to now look to see if we have any questions. We do. Let me see if I can make this bigger so I can see it. The first question is, do we have a tutorial about the FACS, HAZOP, and LOPA software and Excellentia? And we do. We have webinars on it, and we have blogs on it. And if that's something that you want more information on, please feel free. You can look on our website, but you can also email me. And we can get you information if you need more of that. Another question is, what is better, ARITA or SynTef? Actually, ARITA and SynTef are working together to produce the ARITA book. So I would say that since they're working together, that's a great combination. And we're very excited to see their new book coming out shortly. The next question is, it's not quite a question. I don't understand what this means. It just says, because the B10 is not recommended for lambdas for process. If you still have questions, feel free to ask, but I think we probably covered this with the B10 being cycle testing. It's great for high and continuous demand applications, but for process safety or static applications, not dynamic applications, I would say that the B10 is not applicable. The next question, how many FMEDA are necessary for significant on the same product, and say what the failure rates are good? I believe this is asking how we calibrate the failure rates and what are considered good failure rates. We have been calibrating our failure rate database for over 15 years now. And when the FMEDA is done, we actually compare this to the field returns and make sure that the FMEDAs are slightly pessimistic. So we have been doing thousands of FMEDAs. We have been collecting data from thousands and thousands of components. So our database has been studied for over 15 years. What is the difference in time method of the B10 and FMEDA? How is the base time of a FMEDA for the proof of products? The time difference, once again, for the B10 is cycle testing. So it would be high or continuous demand mode. A FMEDA we consider a low demand mode. The next question. How would you explain the difference in safety ratings between the T** rating and the rest of the sources? So this is actually shown on the one graph. We aren't positive what the T** did, but in back calculating, we are assuming it was either done with a cycle test method or just simply using the manufacturer's returns. And as we talked about, most you don't know what the manufacturer considers a failure, and also you don't know what how many were actually returned. So we wouldn't recommend using such a low failure rate, as we talked about in the very beginning. And I'm going to put this bluntly, garbage in is garbage out. If you put in unrealistic failure rates, you're not going to be reaching the skill level that you think you are, and it can put you in a very dangerous situation. How can we estimate the PFD average of mechanical equipment? We have software, Excellentia software, that can estimate the PFD average, and there's also different calculations to do. So you're going to, you can either use our Excellentia and our database to do that. And we actually have blogs and webinars on our website explaining PFD average and what all it takes to calculate this. Oh, and somebody corrected me. Actually, the ARETA has been published. It was available effective the 15th of last month. That is great. Thank you, Roger, for correcting me. We have ours ordered, but we have not received it, so that's why I was assuming that it has not been officially published and released. But we actually have ours ordered, and we cannot wait to read it. We think that it is a very valuable book, and we're excited to see what the newest edition holds for us. The next question, is it possible to still rate a wellhead control panel, a hydraulic panel for oil and gas wells? That would be a, you have to go through the SIL process. You would have to do an FMEDA for the different portions and devices that go into this. Each would be SIL rated, or you would go through the SIL process and receive a certificate for each device that goes into it. Then you would do a SIL verification study to make sure that you are meeting your risk reduction needed and your SIL needed for the whole process. Yes, it is possible to do a SIL verification for an entire system. The next question is, oh, it just went away. Hold on one second. I'm trying to expand it. It was a long question. As a simple question, have you attempted to compare exida dataset to those provided by the old RIAC, PRD, the NPRD, and the FMD? To be honest, Roger, I am not positive. I am newer to exida, but that is a question that I can ask the people that have been at exida longer than I have, and to see if our data set has been compared to the list that you have recommended. I can get back to you and answer on that, so if you would like to send me your email address or email me specifically, it's lstewart, S-T-E-W-A-R-T, @exida.com. The next question is, in my area of responsibility, I am more concerned with the demand or cycle test or test data. The probability of failure to start / actuate on demand. Do you have any potential sources that might be available to capture the risk based on cycles and demands? Yes, we actually have webinars on this subject directly. We have blogs and white papers. So if you go to our either our YouTube channel or our website, we have a lot of information on comparing cycle testing and demand and the probability of failure on this and why it is a dangerous to assume low demand in cycle test. The next question is, we have seen the same catalog product rated at 2 different SIL capability levels. Is it reasonable, all other control factors being the same? I guess my question to you is, is it the same company? Because you have, and it depends on which company certifies it. If all factors are being the same, it would not be reasonable unless it is the architecture is different. You could do a 1 out of 2 architecture and increase the sill, but if everything being the same, no, it is not reasonable. Probably 2 different companies rated it, and it was probably done by different techniques. If we were to rate the product, we would use the FMEDA in our calibrated database. We would go in and make sure, audit the facility and make sure the facility, their documentation, the manufacturing process, that everything is indeed going to meet that SIL level and that you can expect quality out of a certain quality level or SIL level out of the base. You can change the SIL by using it in different architecture, but if everything, all other control factors being the same, no, it is not reasonable to have the product rated at 2 different SIL levels. That would be a red flag if I were you in looking at it. If you have any other questions, please feel free to email me. I've enjoyed all of your questions. Thank you very much, and thank you for attending our webinar. I hope you have a great day.